All right, so now we're going to talk about a slightly different type of optimization and an extremely powerful method to solve problems. So the method is called Lagrange multipliers. And so here's the setup. So we're going to continue the theme of looking at functions of two variables for now, but the ideas will extend to functions of three or more variables. So we have a function of two variables that we want to maximize or minimize. And this function we're going to call the objective function. So the function that we want to maximize and minimize we call the objective function. And f is going to be subject to an equation of this form. So we have a function of x and y equaling to some constant k. And this is called a constraint. And now we could have more than one constraint, but for now we'll just consider, again, functions of two variables for our objective function, and then a single constraint. And so the idea, if we sketch a picture, so we have the x-axis, the y-axis, and now what I'm going to do is I'm going to first of all sketch my constraint curve. So this is just a curve, so maybe it looks something like that, I don't know. So here's g equals k. And then the next thing I'm going to do is I'm going to plot some level curves of my function. Okay, so maybe one is like this. So maybe this is f equals c1. This is f equals c2. Like that. And so maybe I have another level curve. And this level curve maybe just barely touches the constraint, like that. So maybe this is f equals c3. So again, in green, these are level curves. And then here we have our constraint. And so the idea is that, let's say the C1, C2, C3 are increasing. So the largest that f could be and still be subject to this constraint. So notice that we have points here and here where our function is going to be subject to the constraint. We have points here and here, but we can keep increasing all the way until we just barely touch the constraint. Or in other words, the level curve is tangent to the constraint. And we actually have another way to write that. So if we look at the gradient vector of, first of all, the level curve and then second of all of the constraint, they're going to be pointing in the same direction. So where does this maximum or minimum occur for this objective function subject to this constraint? Well, it's going to occur exactly when the gradient vectors point in the same direction. Or in other words, the gradient of f is equal to some multiple of the gradient of g. And so it's not that the gradients are exactly the same. They don't necessarily have the same length, but they are pointing in the same direction. And so I'm signifying that by noting that I could rescale the gradient of g. I can even flip the sign and then have it be equal to the gradient of f. And this number lambda here is called the Lagrange multiplier. And so what is the advantage of doing this, or viewing this problem in this way? Well, when we find the gradient of f, and we set it equal to the gradient of g times this Lagrange multiplier, we get a system of algebraic equations that we can then solve. And when we solve those algebraic equations, the points that we get, the xy coordinate points, that's going to be where either the maximum or the minimum of the functions will occur. We just have to test those individual values and see which is the maximum and which is the minimum. Okay, so things are going to work exactly the same if we have a function of 3 variables, subject to a single constraint. So we have our objective function, f, and then subject to this function g equal to some constant k. Then to solve, to find the maximum and minimum of this function subject to this constraint, we just set the gradient of f equal to lambda, some number, times the gradient of g. And then let's say we had another constraint. So let's say we had h of x, y, z is equal to L. Well, then what I'm going to do is I'm just going to add on a second Lagrange multiplier, call it mu, times the gradient of h. And so now we're going to have another variable that we're going to have to solve for, but we're going to be able to do that. We're going to have in total 5 unknowns. We're going to have 3 equations given by the gradient, and then we're going to have the 2 constraints, 4 and 5. And so you can view this geometrically. It's a little bit more difficult, but you can at least say that the gradient of f lies in the plane spanned by the gradient of g and the gradient of h. So you sort of have to view that in 3 dimensions to fully understand it. But the idea works exactly the same way if there's just one constraint. And theoretically, there could be as many constraints as you want, and you would just keep adding on the gradient of the constraint times another Lagrange multiplier, and you would just keep doing that, and then you would just solve the corresponding system of equations. So that's the idea behind Lagrange multipliers. It's really simple and really powerful, and we'll illustrate how the details go with a few examples. Alright, so here we have a very simple optimization question. So we want to minimize this function, which is our objective function, and then subject to this constraint, x plus y equals 1. But we want to do it in 2 ways. So the first way, we want to actually reduce this down to a 1 variable optimization problem. And then second, we want to use the method of Lagrange multipliers. So we're just going to solve it the way we probably already know how, by reducing to a 1 variable optimization case, and then use Lagrange multipliers just to illustrate how the method works. So method 1, what we would do, we want to optimize this function, minimize this function, subject to this constraint. Well, I can solve and just say y is equal to 1 minus x. But then if I plug this in, I get a function of 1 variable. So if I plug in 1 minus x for y, I get x squared plus 1 minus x squared. Notice this is now a function of 1 variable. And then I take the derivative. There we go. And then I set it equal to 0 to find my critical points. And so I have 2x minus 2, and then plus 2x is 0. Or in other words, 4x minus 2 is 0. And then we can solve this to get x is equal to 1/2. And now notice that if I take the second derivative, what am I going to get? I'm just going to get 4. And so what that means is that my function is always concave down, which means there can only be one minimum. So I know that a minimum is going to occur at x equals 1/2. And so what is that minimum? Well, I'm going to have 1/2 for x. Y is going to be 1 minus 1/2, so also 1/2. And so what is this? 1/2 squared is 1/4. Plus 1/2 squared is another 1/4. So our minimum value actually is 1/2. So that was just a quick calc run review of how you would solve this optimization question. But let's see how it goes with Lagrange multipliers. So what we want to do is realize we have our objective function here. And notice that we have this constraint function that needs to be 1. So we have g of xy is equal to my constraint function, which is x plus y. And we require that g of xy be 1. Okay, so let's set the gradient of f equal to our Lagrange multiplier lambda times the gradient of g. So the gradient of f is 2x, so partial with respect to x, comma 2y, partial with respect to y. And that should equal lambda times the gradient of g, which is 1, 1. Okay, so what we see is we actually get two equations. We get 2x equals lambda for the x coordinate, and we get 2y equals lambda for the y coordinate. And now if we subtract these two equations, we get 2 times x minus y equals 0. But the only way this is true is if x is equal to y. But I know that x plus y has to equal 1. So if x equals y and x plus y equals 1, x equals y equals 1/2. But this is the same thing we got here. So we take f of 1/2, 1/2, and we get 1/2. So we do indeed get the same minimum value. Now it's debatable which one of these methods is quicker in this particular problem. But what is going to be true is that the second method is going to apply to a lot broader range of problems than the first method. And the first method can get extremely messy, whereas the second method keeps things relatively simple and relatively algebraic, as we'll see. All right, so now let's have a little bit of fun. So we want to find the point on the sphere that is closest and furthest away from this point 1, 1, 2. So the function that we're maximizing and minimizing, or in other words, our objective function, is going to be the distance from this point right here. And it's fine if we just go ahead and actually use the distance squared to get rid of the square root. The points that we find will be the same. So the distance squared is going to be x minus 1 squared plus y minus 1 squared plus c minus 2 squared. And our constraint is x squared plus y squared plus z squared, and we need that constraint function to be equal to 1. Okay, so let's set the gradients equal to each other, or equal to a multiple of each other. So the gradient of f, we want that to be a multiple, a scalar multiple of the gradient of g. And so what do we get? Well, the gradient of f is 2 times x minus 1, 2 times y minus 1, and then 2 times z minus 2. And then we have lambda, and the gradient of g is 2x, 2y, 2z. All right. So we get 3 equations out of this. And our fourth equation is going to be that the constraint needs to be 1. And notice that we actually have 4 unknown variables. So our system should be solvable. So the equations we get, I can divide by 2, computing the x coordinates. So I have x minus 1 equals lambda x. I have y minus 1 equals lambda y, and then I have z minus 2 equals lambda z. So if I take these first two equations and subtract them, what I get, so x minus 1 minus y minus 1 is x minus y. And on the right-hand side, lambda x minus lambda y is lambda times x minus y. But this is excellent because I see that either one of two things can happen. Either, well, x could equal y, which makes both sides of this equation 0, so that would be true. Or x and y could be anything, and lambda could be 1. So either x equals y, or a lambda is equal to 1. But what happens if lambda equals 1? Let's look at the first equation. We have that x minus 1 will equal x, but then if I subtract x, I get minus 1 equals 0. But this is a contradiction. So that means lambda equals 1 can't happen. So then it must be the case that x is equal to y. Okay, so now that we know that x is equal to y, let's try to figure out something about z. So if I solve this first equation for lambda, I get lambda is equal to x minus 1 over x. And let me plug that in for lambda in the z equation. So I have z minus 2 is equal to x minus 1 over x times z. Or if I multiply both sides by x, I have zx minus 2x equals zx minus c. The zx's I can cancel, and I get that z is equal to 2x. Well, that's great. Now I know that x equals y, and z is equal to 2x. So now let me plug all that back in into my constraint function. So I have x squared plus y is just x, so another x squared. And then z is 2x, so that's going to be 4x squared when I square z is equal to 1. Or in other words, 6x squared equals 1, or x is equal to plus or minus square root of 1 over 6. And notice that that's also what y is, because x is equal to y. So I get that y is equal to plus or minus square root of 1 over 6. And then z is twice x. So z is plus or minus 2 times the square root of 1 over 6. All right, and so notice that if x is plus square root of 1/6, y will be plus square root of 1/6, and z is plus 2 times the square root of 1/6. And so the closest point to this point 1, 1, 2 is going to be the positive solution. So the closest is going to be square root of 1/6, square root of 1/6, 2 square root of 1/6. And that's because that's the positive point. That's the point in the positive first octant, which is going to be in the same octant as this point. And then the furthest point is going to be actually the negative solution. So that's going to be minus square root of 1/6. This is going to be on the other side, or the opposite side of the sphere. Minus 2 square root of 1/6. So here's my closest point, here's my furthest point. Okay, so here we have a Lagrange multiplier problem where we have two constraints. So here's our objective function that we're trying to minimize. And then here are our two constraints. So we have g of x, y, z is equal to x plus y plus c, and we want that to be 1. And then our second constraint is h, which is x squared plus y squared equals 1. So we also want this constraint to equal 1. And so recall, if we set our gradients, we require that the gradient of f be kind of a linear combination of the gradients of the two constraints, is the way I think about it. So we have these two numbers, lambda and mu, that I don't actually know what they are. So I have this. Okay, great. So what does this mean? Or what does this tell me? So the gradient of f is 1, 0, 1. And then we have lambda times the gradient of g, which is 1, 1, 1, plus mu times the gradient of h, which is 2x, 2y, and 0, like that. So notice that we get three equations. We get 1 is equal to lambda plus 2 mu x. We get 0 is equal to lambda plus 2 mu y. And then finally we get 1 is equal to lambda. But that's great because now we actually know what lambda is. So then if we plug in lambda equals 1 into this equation, we get 1 is equal to 1 plus 2 mu x, or 0 is equal to 2 mu x. So either, we're just doing it again by cases, mu is 0, or x is 0. So there's our two cases that we get by solving this equation. Because the product of those two variables is 0, one of them has to be 0. But if mu is 0, what happens? Well, let's see. So if mu is 0 here, then we get, so I'm looking at the second equation, I have 0, lambda is 1, and then I add 0, but that's a contradiction. I get that 0 equals 1. So mu can't be 0 because it leads to a contradiction here. So that means x is 0. All right, so if x is equal to 0, what does that mean? Okay, well, if x is 0, let's look at this constraint here. If x is 0, then I have y squared is equal to 1. But that means y is equal plus or minus 1. But that tells me exactly what z is. So x is 0, y is either plus or minus 1. So in the case that x is 0 and y is 1, well, I plug in 0 and 1. So I have 1 plus z equals 1. So z must be 0. So here's 1 point. That's the solution. And then if y is negative 1, I have negative 1 plus z equals 1. But in that case, z is equal to 2. So my minimum is going to occur at one of these 2 points. So what is f of 0, 1, 0? Well, it's just going to be the z coordinate 0 plus the x coordinate 0, so it's 0. And then 0, negative 1, 2, the function is just the x coordinate plus the z coordinate. This is 2, so here is the minimum of our function. All right, so we want to maximize the volume of an open-topped box. So let's draw our box here. And the constraint is that we want the box to have, or to be made with materials that have an area of 48 inches squared. Okay, so it's open topped. So this is solid, all this is solid, but the top is open. And let's say that the height here is z, and then the front edge is x, and then this long length is y. So our objective function, f of x, y, z, is the volume. That's what we're trying to maximize. So x times y times z. And what is our constraint? Well, our constraint is the surface area. Well, what's the surface area of this box? Well, I only have one side, the bottom side, that has area x times y. I have two sides that have area x times z, the front and the back. And then I have two sides that have area yz, this right side and the left side, like that. So I want this constraint to be 48. So let's set up our Lagrange multiplier equation. So the gradient of f should be lambda times the gradient of g. The gradient of f is, okay, so the x derivative is yz, and then xz, and then xy, partial with respect to z. Okay, and that should equal lambda times partial with respect to x is going to be y plus 2z. Partial with respect to y is going to be x plus 2z. And then partial with respect to z is going to be 2x plus 2y. Okay, so I get three equations from this. I get yz is equal to lambda x plus 2 lambda z. And then I get xz is equal to lambda x plus 2 lambda z. And then finally, I get xy is equal to 2 lambda x plus 2 lambda y. Okay, so the first thing I'm going to do is I'm going to subtract the first two equations. So yz minus xz is going to be z times y minus x. And then lambda x minus lambda x is gone. And then I have 2 lambda, let's see, something's not great right here. This should be y, that's what's wrong. Yeah, so let's see, yz is equal to lambda y, lambda times y, plus 2 lambda z. Okay, and when I subtract here, I get lambda times y minus x, and then the 2 lambda z minus 2 lambda z, that's 0. And so looking at this equation, either one of two things is the case. So either y equals x, in which case both sides of this equation are 0, or z is equal to lambda. But z is equal to lambda is going to be a problem. Because let's look at this equation up here. So if z is equal to lambda, this is xz and this is xz, and this is 2z squared, I can subtract this. I get 2z squared is equal to 0, or in other words, z must be 0. But I'm trying to maximize the volume of this box. So if the height is 0, the volume is 0. And there's no way that's going to be the maximum volume. So this cannot be the case. So it must be the case that y is equal to x. Okay. But if y is equal to x, let's look at this equation down here. This is going to say then that x squared is equal to 4 lambda x. Now by a similar argument, I can assume that x is not equal to 0, otherwise the volume is 0. So I can actually solve for lambda. I can divide by x, and divide by 4, so I get lambda is equal to x over 4. Great. So now I'm going to plug this back into this equation over here. So I have xz is equal to lambda x, which is x squared over 4, so x times x over 4, plus, so 2xz over 4, so that's just xz over 4, like that. Okay, look right, x over 4 there. Oh, sorry, xz over 2. There we go, because it is 2 times xz over 4, so xz over 2. Okay, let's multiply through by 2, so I get 2xz equals x squared over 2 plus xz, or in other words, xz, we can move this over, and then multiply by 2 is equal to x squared, but x is not 0, so it must be the case that x is equal to 2z. So we have x equals y, and x equals 2z. Okay, so let's just plug in what that means. So x equals y equals 2z, so that's going to be 2z times 2z, which is 4z squared, plus 2 times 2z times z, so plus 4z squared, and then again 2 times 2z times z, 4z squared, equals 48, or in other words 12, z squared is 48, or z squared is equal to 4. And of course, when we take the square root here, we want to take the positive square root. So we get z is equal to 2. But if z is equal to 2, x is equal to 4, right? So x is equal to 4. X is equal to 4. And then, since x equals y, y is equal to 4. So these are the dimensions that will maximize the volume. And what is the maximum volume? Well, it's just going to be f of 4, 4, 2, which is 4 times 4 times 2, which is 32 inches cubed.